Welcome. We are going to be doing chapter number 15. The title for this particular chapter is Chemical Equilibrium. This particular chapter has been divided into 3 units, and each unit is co-linked to one another. Therefore, you have a full picture of the particular entire chapter. Just before I start sharing my screen with you, I just want to let you know that towards the end and in between the topics, there will be some self-study questions. Please try to answer them to ensure that you have understood the concept for that particular section of the topic studied. This way you will have an updated information, and it will make it easy for you to understand the topic. Should you need some other assistance, of course, the university provides the TAN services. And in addition to that, you have an audio textbook for this for the General Chemistry 102. It is titled as Chemistry and Chemical Reactivity by Kotz, K-O-T-Z, and Treichel, T-R-I-E-C-H-E-L. The edition is the 11th edition. And also the PowerPoints associated with this particular chapter is available in detail to a larger extent. And my own PowerPoints are shortened versions which contain the most important topics and sections that you need to know in order to proceed forward. Remembering that chapter number 15 and chapter number 16 are quantitative aspects of chemical equilibrium, and they are continued together, one after the other in sequential order. And with this, I'm going to start the PowerPoint presentation and let you know that there are 3 units, and this is the first unit. Now, Unit 1, Chemical Equilibrium, the chapter is 15. The content for this particular section of Unit 1 is differentiate between equilibrium and dynamic equilibrium. Principle, rate of forward reaction is equal to rate of reverse reaction. The law of mass action by Peter Wage and Cato Goldberg. Then we are going to write an equilibrium constant expression, interpretation of the magnitude of K, reaction coefficient Q, Kc, and conditions to determine if a reaction is in equilibrium, and the relationship between Kc and Kp, wherein for Kp is used for gases, and we know that the relation between gas is given by the ideal gas equation as well as Boyle's law. Now, in general, chemical equilibrium, all reactions are generally considered reversible, at least in theory. The concept of equilibrium is fundamental to chemistry. The general concept for equilibrium was introduced in chapter 3 to explain the limited dissociation of weak acids. The goal of this and the following chapter is to consider chemical equilibria in quantitative terms. The extent to which that equilibrium lies, whether it is a product favored versus a reactant favored reaction. Equilibrium. At the macroscopy level, there is no observable changes that take place. However, when we go to the molecular level, there is dynamic changes occurring, and the dynamic changes occur in the forward and reverse direction, and they are equal, and therefore we can write based on kinetics that the rate of the forward reaction equals the rate of the reverse reaction. Before we go into the actual theoretical aspect of this and derive the quantitative measurements and implications, I wanted to show you a general chemical dynamic equilibrium reaction that is there. And this is a very common reaction which occurs. Now, sodium bicarbonate solution and calcium chloride solutions are mixed together and a solid is produced with the release of carbon dioxide. And that is the set shown on the extreme left of this particular slide. In the middle slide shows that if dry ice is added to this solid, to the slurry of calcium carbonate is precipitated out. Now, as you add sufficient quantity of dry ice, what happens to the slurry is that the slurry dissolves, giving rise to a clear solution containing calcium ions and bicarbonate ions. Now, even though the solid is there, this is an example, typical example of a reversible dynamic equilibrium. The law of mass action, formulated by Cato Goldberg and Peter Wage in 1864, states that the rate of a chemical reaction is directly proportional to the product of the concentration of the reactants at equilibrium, and the ratio of the products to the reactants is a constant. This is the concept for writing the equilibrium reversible reactions. Now, if you have a reaction which consists of a single component, that's a unimolecular first order reaction basically, and it gives a product B, one product, then the rate of the forward reaction is equal to the rate of the reverse reaction. Rate of forward reaction is equal to rate of reverse, and the rate of forward reaction is expressed in terms of the concentration of the reactant A. So Kf multiplied by the product of the concentration for A must equal Kr, the specific rate constant for the reverse reaction, multiplied by the concentration of B, where in this case, at the time of the reverse reaction, B becomes the reactant. But one has to remember that Kf is not equal to Kr, neither are the concentrations of A and B equal. Therefore, if we arrange this equality reaction, Kf product concentration A equals Kr concentration B, by selecting the concentration terms on one side and of the equality sign, and in the terms independent of concentration on the other side, then we get the ratio of B over A equal to Kf over Kr, a constant, and this is called as the equilibrium constant. Should there be more products, more reactants and more products, the concept is the same. The only thing is that the concentration of either the product or the reactants, they are all raised to their respective stoichiometric moles in a balanced equation, ultimately leading to the equation that Kc is equal to products over concentration of the products over the concentration of the reactants. Now, if this system is at equilibrium, then the equilibrium constant is given at a particular temperature. And so we have two conditions. Basically we will have three conditions. One, where when K is greater than 0, then it is a product favored reaction. When K is less than 0, then it's a reactant favored reaction. And the third condition is when K is equal to 0 or almost 0, approaching 0, then the system is considered to be at equilibrium or reaching equilibrium. Very large number of experiments have shown this to be true at equilibrium. But the rules for writing K and its usefulness or purpose. Generally, when we write K, we include gases and solutions, but exclude solids, pure liquids, and water. Values of K are dimensionless. Each concentration is raised to the power of its stoichiometric coefficient in the balanced chemical equation. All concentrations are equilibrium values. Product concentrations appear in the numerator. Reactant concentrations appear in the denominator. The value of K depends on temperature. Concentrations can be calculated for aqueous solutions in terms of Kc. Concentrations for gaseous systems use Kp, where P stands for the partial pressures. K indicates whether reaction is product or reactant favored. Now, writing and manipulating K. Solids and liquids are never appear in the equilibrium expressions. So, for example, S sulfur solid plus oxygen gas react to give SO2 gas, and this is an equilibrium reaction in which the equilibrium constant K is the ratio of the concentration of sulfur dioxide divided by the concentration of oxygen. As you can see, the concentration of sulfur does not appear. Why? Because at equilibrium concentrations, the reactants and products are not dependent upon the concentration of the solid present, and therefore we assume that the solid is essentially a constant. Why do not we include water? For the same reason. Water is in large amount. The concentration of the H and OH ions are extremely small, and therefore they do not generally affect the rate of the reaction. That is, as stated before. Now, when we write the equilibrium constant for any given reaction, we look at whether are we writing the constant in terms of concentration, as you can see on the left-hand side, and the same expression is denoted on the right-hand side in terms of partial pressure. Remembering that partial pressure for any gas is the concentration of the gas times RT. Why? Because the ideal gas equation says PV is equal to nRT and N divided by V, the number of moles. And if the volume V is in unit of liters, then it is the concentration term. And from this, we see that both Kc and Kp are related by the number of terms for RT that is present in the equation. Otherwise, we can if we know Kp, we can calculate Kc directly from the relationship. The interpretation of K can tell us if a reaction is product favored or reactant favored. And a typical example is, of course, that of ammonia gas form produced by the combination of nitrogen and hydrogen gas, giving rise to 2-ammonia. From the expression and solution for this particular problem, we see that K is very, very large, and therefore this is a product favored reaction. What does the magnitude of K tell us? That if K is greater than 1, then it lies to the right, product favored. If K is approximately equal to 1, then it is reactant at equilibrium. And if K is far less than 1, then it lies to the left and it is a reactant favored. What happens? Now, all this time we have been assuming that the reactions are at equilibrium. What happens if the reaction is not in equilibrium? When the system is not in equilibrium, then the expression for writing the K expression is the same, except that the term equilibrium constant K is replaced by Q. The concentrations are not at equilibrium, therefore Q is equal to system. If Q is equal to K, then the system is at equilibrium. If Q is not equal to K, then the system is not at equilibrium. And so we have the same. Generally, we always write the concentrations as in terms of the subscript EQ, indicating that it is at equilibrium. If it is not an equilibrium system, then we do not write a subscript, automatically indicating that the system is not in equilibrium. Now, because we have Q and K, again, the same conditions apply. Q greater than K, product favored. So in order to reach K, what must happen is the concentration of the reactant must increase, the concentration of the product must decrease so that Q approaches K. When Q is equal to K, there is no shift in the direction of the equilibrium. It remains at that position. But when Q is less than K is less than Q, then reactants must be converted to products to reach equilibrium, thereby increasing the concentration of the product, decreasing the concentration of the reactant. Now here it is a study review question. Just go through it. You're given the concentration. You have to plug it into the equation for K and then answer the two questions that are there. The expression for the K. Generally, whenever we do the steps for determining K, we write the expression, provide the initial concentration, see what change occurs over time, and then what happens to the concentration of the products with time, and then use that information to calculate the K value. And before we proceed on any further, I want to introduce how we use the K or Q calculation method. Always, we generally try to put it under either the ICE table or what we call as the RICE table, because RICE, where R stands for the reaction. So right on top, you see the reaction on the little chart over there, table. Below that, we have the initial concentration in moles per liter. The C represents the change in concentration over time till equilibrium is established. E is the equilibrium constant for each component when equilibrium is established. And so for the given example, I plugged in the numbers, and so you can see how you get. Now, in the problem, only the initial concentration and the equilibrium concentrations were given, so you could calculate the K. But I introduced to you how to get if the equilibrium concentration is given, and if you know the initial concentration, then one is able to calculate the change in concentration as shown on the top as the initial concentration minus the equilibrium concentration will provide information as to the extent of change in the concentration of the reactants and products. The changes are always in terms of the moles of each of the components in the balanced equation. This is another example with NOA, and then you have 3 sets of self-study questions that are there. So there are 5 questions that are self-study questions for you. Try to do them. And with that, we finish the unit number 1. And then as we finish unit number 1, I want to introduce what we will be doing in unit number 2. In unit number 2, we are going to calculate the equilibrium constant K. Next, once we know how to calculate it, then what are the approximation techniques to be used when we calculate equilibrium constants? And of course, finally, if the equilibrium changes in concentration are too high, then we have to use the quadratic equation. And with that, I'm going to stop and